Chapter 5.4 is trigonometric functions of real numbers, and this section is going to be covering the unit circle. So starting with the unit circle here. So the unit circle is essentially like the basic or parent function for circle equations. The equation is x squared plus y squared equals 1. So if this is an equation in standard form, if you recall, you can figure out the center of the circle and the radius when it's in standard form. The center in this case is going to be the origin, 0, 0. And the radius is going to be 1. So all the unit circle is just a circle where the center of the circle is at the origin and the radius of the circle is 1. So it's obviously graphed right here on the right. So we can see where the center is, we can see where the radius is, or what the radius is. So if the radius is 1, that means we have these 4 coordinates right here, crossing through all of the axes at 1 and -1. So you're probably thinking, how does this relate to trigonometry? So what we can do is, let's say we're on the unit circle. Let's say we're some xy coordinate right here. What we can do is we can draw an angle where the terminal ray cuts through that coordinate. So we have the initial ray on the x-axis and then the terminal ray cutting through that point. So when we do this, we have this angle that opens up, and that's our theta. And we can create a right triangle by vertically dropping down a line from the coordinate to the x-axis. And it creates a right triangle. So once we do that, we can think of this in terms of right triangle trigonometry. We know that the length of the vertical side of the triangle is y, because that's the y coordinate, that's the vertical distance. We know the horizontal distance is x, because that was the x coordinate. And then we can figure out the radius. We actually know the radius because this is a circle with the radius of 1. So that means on the unit circle, the hypotenuse is always going to equal 1. So taking a look back at the unit circle equation, it's x squared plus y squared equals 1. That is exactly what the Pythagorean theorem would tell us for this triangle that we created. Okay, so now relating this to our trigonometric functions, we can use our SOHCAHTOA and our reciprocal identities, and we can figure out that sine of theta is opposite over hypotenuse. So sine of theta would be y over 1, which is y. Cosine of theta would be x over 1, which is x, and so on. So on the unit circle, we actually have these identities right here. Sine of theta equals y, cosine of theta equals x, tangent of theta is y over x, cosecant of theta is 1 over y, secant theta, 1 over x, cotangent theta, x over y. So x and y here are just the coordinates. So when you're given an xy coordinate on the unit circle, the xy coordinate is going to just be cosine of theta, comma, sine theta. Okay, so let's see some of these important angles on the unit circle here and try to explain it. So if you have this memorized, then you're in really good shape for most of these questions. If not, on the next page or whenever it is, I'll describe how you can fill this in with only memorizing several different numbers. Okay, so for this, for the unit circle here, let's take a look going in order. So let's pretend like we have an angle. We have our initial ray right here, and let's say the terminal ray is right here, where the angle is 30 degrees or pi over 6 radians. So if we have an angle of 30 degrees, that means it's cutting through this coordinate. The coordinate that it's cutting through is radical 3 over 2, comma 1/2. So the reason why that's useful is because now, based on the previous page, we know that cosine of, in this case, 30 degrees equals the x coordinate. So that means cosine of 30 degrees equals radical 3 over 2. And then since we also know that sine of theta on the unit circle, in this case sine of 30 degrees, equals the y coordinate, that means sine of 30 degrees equals 1/2. Once you have these two, once you have cosine and sine, you can figure out every other trig function of 30 degrees by using your identities, so the reciprocal identities and the quotient identity for tangent. Okay, so that's why this is so useful. So then for like the next one, for 45 degrees, if we have an angle of 45 degrees, that would be right here. 45 degrees or pi over 4 radians. That means cosine of 45 degrees is the x-coordinate, radical 2 over 2, and sine of 45 degrees is the y-coordinate, radical 2 over 2. Okay, and then we can keep on going. As you can see, we can have 60 degrees, 90 degrees, 120 degrees, 135, and it loops all the way around to 360 degrees. So some ones that are pretty important here are going to be the ones that are directly on the axes. So we can see from this first one on the x-axis, that would represent 0 degrees, right? If it's directly on that x-axis. So sine of 0 degrees, sine of 0 degrees will be the y-coordinate, so sine of 0 degrees is 0. For the one up here on the y-axis, that's going to represent 90 degrees. Sine of 90 degrees, or pi over 2 radians, equals the y-coordinate, so sine of 90 degrees equals 1. And we can keep on going around here and say that sine of 180 degrees, which is sine of pi radians, is 0. And I'll just fill in the other ones. So sine of 270 degrees, negative y-axis is negative 1. And sine of 360 degrees is also 0. And it's going to repeat in that pattern. So for these ones, we couldn't really find a reference angle like we did in the previous section. So these are ones that the unit circle can definitely help us out with a lot. So I'll write the cosine ones on the left here. So we know that cosine of the angle is going to be the x-coordinate that it crosses through on the unit circle. So cosine of 0 degrees is 1. Cosine of 90 degrees is 0, cosine of 180 degrees is negative 1, cosine 270 degrees is 0, and cosine of 360 degrees is 1. So obviously these aren't all of the important ones, but they're most of them. And once again, if you know these two, sine and cosine, you can figure out tangent, cotangent, secant, and cosecant using the identities. And make a little note, also know these angles when they're in radians as well. So on the next page, I'll go over how we can, a useful technique for how to fill this in just from scrap paper, just when everything's completely blank. So notice there's a ton of symmetry here. Notice these numbers. We have radical 3 over 2, 1/2, radical 2 over 2, and those numbers pretty much repeat, right? Some of them are negative, but overall, they repeat themselves over and over again. And also looking at the angles. So the first quadrant here, we have 30 degrees, then we have 45 degrees, 60 degrees, 90 degrees. So that was plus 30, plus another 15 to get to 45, plus another, oops, not 30, plus another 15 to get to 60, and plus another 30 to get to 90. So that's going to repeat over and over and over again also, that pattern. So that's how we can find the other angles. So let's actually fill this in now. So this is how to fill this in. Okay, so each quadrant here is going to have 3 angles going through it. Okay, so you get 3 lines going through each quadrant, representing the different angles in that quadrant for each set of XY coordinates that it's going to be passing through. So for the only other thing that we need here is to have a few numbers memorized. So the numbers to memorize are going to be 0, zoom in a little bit, 0, 1/2, radical 2 over 2, radical 3 over 2, and 1. So this is actually easier than it looks to memorize. 0, you can think of everything having a denominator of 2. It would be radical 0 over 2, which is 0, radical 1 over 2, which is 1 over 2, and then radical 2 over 2, radical 3 over 2, and then radical 4 over 2, which is 2 over 2, which is 1. So there is a lot of symmetry here. So there's those values you need to know, and then the other values would be the angles. So it would be 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. So I mentioned it on the last page, but this will help us fill out the other angles because we know it's going to be plus 30, plus 15, plus 15, and plus 30. So that pattern is going to repeat over and over and over again. Okay, so let's start filling this in now. So we know the first angle here is going to be 30 degrees. So obviously know that this is also pi over 6 radians. The second one's going to be 45 degrees, 60 degrees, and then the right angle will give us 90 degrees. So now filling in the coordinates right here, we have 3 to choose from. Obviously we're not using the zeros or the ones that I wrote up here because those are for the axes themselves, the x and y axes. So for this first coordinate, that's on 30 degrees. We know that the x coordinate is going to be the largest other than 1 because it's most to the right. The largest number that we wrote down is radical 3 over 2. So we knew that had to be the x coordinate. That is the smallest y coordinate. And the smallest y coordinate other than 0 is 1/2. So we know that first coordinate has to be the xy point, radical 3 over 2, comma 1/2. For the next one is going to be, it's actually the midway point for that arc. It is the one that is halfway, the halfway point for the x's. So other than 0, it's the second largest x, which means it's going to be the radical 2 over 2 for the x coordinate. For the y coordinate, it's the same thing. It's going to be the second largest y coordinate, which is also radical 2 over 2. Okay, and then for this last one here, for the last point on the circle, it's the largest y coordinate and the smallest x coordinate. That means it's going to be the coordinate 1/2, comma, radical 3 over 2. Okay, so once you know those ones, and like I mentioned, filling in the other ones should be pretty doable. For this next arc over here, so now we're in the second quadrant, we know we're going to have to add 30 degrees, so I'm going to be using this concept that I wrote up here, where now it's just going to be adding 30, and then add 15, add 15, add 30 over and over again. So 90 degrees plus 30 degrees is going to be 120 degrees. So that's going to be that angle right there. And now we're adding 15, which gives us 135 degrees. Add another 15, 150 degrees. And then obviously, when we get down here, that's going to be 180 degrees. Okay, so now for filling in what coordinates these are passing through, we have to know that we're going to be using those same values, 0, 1/2, radical 2 over 2, radical 3 over 2, and 1. So that first one for 120 degrees, that is the largest y value, which is going to be radical 3 over 2. For the x value, it's going to be the smallest x value because it's the smallest to the left, which is going to be 1/2. But what we have to keep in mind here is that it's going to be negative 1/2 because we are in the negative x direction. So this is in the negative x direction, so the x values are negative, the y values are still positive. And then the one in the middle is always going to be radical 2 over 2 and radical 2 over 2, But once again, we have to remember that we're in the negative x direction. So the x is negative. And for 150 degrees, it's going to be the largest x value. So that's the radical 3 over 2. And the smallest y value, which is 1/2. Okay, and now for the third quadrant, I'm just going to throw in 0 degrees right here. It's going to be the same thing. We're going to be adding 30 degrees and then adding 15 degrees and then adding 15 and then adding 30. So 180 degrees plus 30 is 210 degrees. Adding 15, that's 225. Adding 15, that's 240. And then adding 30 gives us to 270 down here. And now filling in these 3 points. So both of the xy coordinates are going to be negative here because we're in the third quadrant. That's negative x, negative y. So for the x coordinate first, that is the furthest x coordinate away from the origin. So that's going to be the radical 3 over 2, and it's negative. And it is the smallest y coordinate, so it's negative 1/2. So just always keep in mind that the radical 2 over 2 are together in the middle, and then the radical 3 over 2 and the 1/2 are always together. So the next one's going to be, with that being said, negative radical 2 over 2 and negative radical 2 over 2. And the last one is going to be negative 1/2 and negative radical 3 over 2. It was the smallest x coordinate and the largest y coordinate. Okay, and then for this last quadrant here in the fourth quadrant, we're going to add 30 degrees to 270. That gives us 300 degrees. We're going to add 315 degrees, and add 15 again. That's 330 degrees. And obviously, the next one's going to be 360, but that would be adding another 30. So that one's 360 degrees, which is coterminal angle with 0 degrees. Okay, and I'll just pause and fill out those remaining 3. And we get those values right there. And keep in mind the x values in the fourth quadrant are positive and the y values are negative. Okay, so this is the unit circle. So I just wanted to show that we can actually fill this out. And obviously make sure you know the angles in radians also. I just put them in degrees so it wasn't too cluttered. And the reason why this is so useful is because we can now remember that cosine of theta equals the x coordinate and sine of theta equals the y coordinate. So once you know those, then you know sine of 210 degrees, you know cosine of 330 degrees by just looking at those coordinates on the unit circle. And for like the 5th time, once you know these ones, you can figure out tangent and all the reciprocals also. Okay, so let's do a couple examples where we're using this idea here. So let's find all the trig functions of theta for the coordinate negative 1/2, comma, radical 3 over 2. So if we were not using the idea for the unit circle here, negative 1/2 radical 3 over 2, we know that would be in the second quadrant, but on the unit circle, that's going to be right here. So we can do the same method that we did in a previous chapter and draw a terminal ray through it. And if we want to, we can create a right triangle and drop down vertical line to the x-axis and say that the vertical distance is the y-coordinate, which is radical 3 over 2. Horizontal distance is the x-coordinate, which is negative 1/2. Since we're on the unit circle, though, it's nice and easy. We don't have to do Pythagorean theorem. We know that the hypotenuse is just going to be equal to 1. Okay, and then previously we said we can use the reference angle to help us do this. So let's not do it that way exactly. What we can say here is sine of theta is going to equal the y-coordinate, which is radical 3 over 2. because we're on the unit circle. And we know that cosine of theta equals the x-coordinate, which is negative 1/2, once again because we're on the unit circle. So once we know these, let's just use the identities to find the other ones. So we know that tan theta is sine theta over cosine. That's radical 3 over 2 divided by negative 1/2. When we divide those, the denominators will cancel. We're going to be left with negative radical 3. Okay, so that's just dividing fractions. So that would be keep, change, flip. Keep the first one the same, change the multiplication, reciprocate the second one. And next for cosecant theta, it's the reciprocal of sine. So the reciprocal of sine is going to be 2 over radical 3. When you rationalize the denominator, we should get 2 radical 3 over 3. For secant theta, the reciprocal of cosine, which is negative 2. And then lastly, for cotangent theta, the reciprocal of tangent, which would be negative 1 over radical 3. We have to rationalize that denominator. We get negative radical 3 over 3. Okay, so pretty simple if you know the unit circle shortcut. So let's do another one. So we want to find all the trig functions of theta for the coordinate radical 2 over 2 comma negative radical 2 over 2. So that's going to put us into quadrant 4. It's going to put us about right here. So we can draw our rays through it. We can create a right triangle. And we know that this is our angle theta. We know our reference angle is right in here. We can fill out the sides of the triangle using the coordinate. We know that this is going to be radical 2 over 2 for the horizontal distance. Vertical is negative radical 2 over 2. And it's a unit circle, so we know the hypotenuse is 1. If we didn't, we use Pythagorean theorem, we would get 1. Okay, so let's use the shortcut though once again. So let's find sine of theta. So sine of theta is going to be the y-coordinate, which is negative radical 2 over 2. Cosine of theta is going to be the x-coordinate, which is radical 2 over 2. Tan theta is going to be sine over cosine. They cancel, and one of them was negative, so we're just left with negative 1. And now for the reciprocal identities. Cosecant is the reciprocal of sine. After we rationalize the denominator, we would get negative 2 radical 2 over 2. We end up getting just negative radical 2, so that one's simplified nicely. For secant theta, it's the reciprocal of cosine, and we would end up getting this to simplify to just radical 2 after we rationalize the denominator. For cotangent, the reciprocal of tangent, reciprocal of negative 1 is just negative 1 again. Okay, so if you have to take the time and actually write out these identities and do them in multiple steps, that's fine. I'm just skipping over them because we've already done them. Okay, so let's do 2 more here. So we'll do 2 more and then we'll mention the domain and range, and that's it for this section. So let's find all trig functions for theta when theta is pi over 2. So when theta is pi over 2, this is obviously a little different how the last ones were worded. We can figure out what coordinate it crosses through when the angle is pi over 2 radians. The angle that it passes through is going to be 0, 1. So that's the coordinate on the unit circle that the terminal ray crosses through. So the point of that is now we can figure this out because we have a coordinate, so we can do that shortcut method. So sine of theta, I'm just going to put in the actual angle here because it's given to us. Sine of pi over 2 equals the y-coordinate, which is 1. Cosine of pi over 2 equals the x-coordinate, which is 0. Tangent of pi over 2 is going to equal sine over cosine. That's 1 over 0. We cannot divide by 0, so this is undefined. Cosecant of pi over 2 is the reciprocal of sine. Reciprocal of 1 is 1. Secant of pi over 2, reciprocal of cosine. 1 over 0, can't divide by 0, that's undefined. And for cotangent pi over 2, So putting a little thought into this one, the reciprocal of something that's undefined, if we are dividing by 0, that means it's undefined. If we reciprocate that, the 0 will then be in the numerator, which means it will be equal to 0 for cotangent of pi over 2. Also, just use the fact that cotangent is equal to cosine over sine, using that quotient identity, which would be 0 over 1, which is 0. Okay, so doing one more of these ones. So let's find all of the trig functions when theta is 3 pi over 4. So 3 pi over 4, if we were to draw the angle out for it, that would be in quadrant 2. And we knew that because that's 3/4 of the way to a straight angle of pi. So this would be our theta right here. So on the unit circle, if we're trying to use the shortcut, we could totally use the triangle method from before once we find that coordinate. But once we find the coordinate, we can just use that shortcut method since we're on the unit circle. So we have to figure out what that coordinate is that it's crossing through. So scrolling back up to the unit circle here. So 3 pi over 4, that is right here. The coordinate that that's crossing through is negative radical 2 over 2, comma, radical 2 over 2. So filling that in right here, negative radical 2 over 2, comma, radical 2 over 2. So we know that this angle on the unit circle is a coordinate, is passing through the coordinate, where x is negative radical 2 over 2, y is radical 2 over 2. So once we know that, we can use the shortcut, and we can say that sine of 3 pi over 4, since that is our theta here, sine is the y coordinate, cosine is the x coordinate. Keep in mind that this also makes sense for what trig functions are positive and negative in which quadrant. So tangent is sine over cosine. The denominators are going to cancel. So will the numerators, because it's the same thing. We're just going to be left with negative 1. For cosecant of 3 pi over 4, the reciprocal of sine, after we rationalize the denominator, we're going to get just radical 2. The reciprocal of cosine for secant, we're going to get negative radical 2 after we rationalize that denominator when we reciprocate it. And for cotangent of 3 pi over 4, the reciprocal of negative 1 for tangent just gives us negative 1. Okay, so obviously really important by this point to make sure you know the reciprocal identities and the quotient identities. So also, I think I mentioned this at one point, but when you're thinking about doing these problems with any sort of trig problem, I recommend thinking about it in terms of right triangle trigonometry, the unit circle, and in terms of their graphs. So those 3 different ways, and we'll get into the graphs, I believe, in the next section. Okay, so for this last page here, it's just the domain and range of sine and cosine. So the domain and range of sine and cosine. So theta here represents the domain. So you can see that the domain is negative infinity to infinity. That's because theta kind of represents our x values for the domain. So the domain is all real numbers. The range, and thinking in terms of sine, and when we're thinking about the unit circle, sine of theta is the y coordinate. So sine of theta is going to be from negative 1 to 1. So sine of theta is the range of the unit circle. And cosine of theta, the range of cosine of theta would equal the domain of the unit circle, because cosine of theta equals the x values. So the range of both of these is going to be from negative 1 to 1, including the 1. Okay, so it's kind of nice for sine and cosine because they both have the same domain and both have the same range. Okay, so that is it for 5.4.